No, let's do math.
So what we're going to do is an experiment in a couple of ways. This is the first time I've ever done a wrangle with teachers, and it's also the first time I've ever tried a wrangle by Zoom. I suspect it would have made a lot more sense to do it with teachers at an in-person workshop so we could sit and talk and work. So the first part of the wrangle is to spend some time working with colleagues trying to solve the math problems. Welcome back, everybody. We do these wrangles with students, and what we found is it's useful to, for instance, give the students a couple problems a day, a week, and you can divide the students into teams, and you let the students work on them and think about them in their teams and discuss together. And when you're helping students, you don't give them the answers because you want to know that, but you can give problem-solving suggestions, and you can give suggestions about how to write and present and say, hey, you want to write this up. One of the goals of this wrangle is to just encourage and teach students how to have a respectful discussion about something. Mathematics and a math problem should not be very contentious, but there definitely are right and wrong answers. And so what we're going to do now is model exactly what we do with the students. Typically, we'll do a coin flip, but since we randomly assigned the rooms, team one is going to have the option to challenge team two to one of these four problems. Team two will then either accept the challenge and somebody will present the answer, which they can do a screen share if they want to send something to me to put graphics to talk, or they can just talk about it. I'll try to take notes. They'll have 5 minutes to present their answer. Then, or they could decide not to present the answer and bounce it back, which then will make the problem worth more points. Instead of worth 7 points, it'll be worth 10 points. And then team one will present the answer. After the answer is presented for 5 minutes, there's up to 2 minutes for the second team, the other team, to discuss and see if the answer is correct, if all the reasons were given and fully justified, or if there were any gaps, and then they make a rebuttal. If it's just correct, they could say, good job, yay. If there's something amiss with it, or if they didn't say something, they say what's wrong and why what was saying was wrong or missing. They don't have to give an answer. And then the judges, which in this case will be me, divides up and gives points to the two teams and possibly the judges if nothing is listed. And then the team that just finished solving a problem challenges the other team, and you go back and forth. So let's say give this a go. So team one. Quick discussion, like 30 seconds. What problem do you want to challenge team two to solve?
Daisy, could we do number two?
You're challenging them to number two?
Yeah, we did number one all together as a group meeting.
Okay, so you're challenging the other team to solve this problem. So team two, you've been challenged to solve problem two. You can either accept the challenge and present your solution, or you can bounce the challenge back to team one and say, no, you do it. But if you bounce it back to team one, it's worth more. So team two, do you accept the challenge or do you bounce it back?
I think we'll accept this challenge.
Awesome. And so can I help with presenting, or who's going to present? Some of you, if you want to share a screen or send me a text, me a graphic, or describe. And so I'll give you like 30 seconds to help think through how you're going to present, and I'll set the timer. You'll have 5 minutes to actually present once we go.
Yeah, I have I have it here on paper, and I tried to email it to myself so I could present it on screen, but the email hasn't come through yet.
Are you?
So.
Somebody looks like it's doing a whiteboard. That looks
Perfect.
clear. Okay, so
Okay, awesome.
you ready to go? Shall I?
So what we decided to do,
I'm starting the timer then.
okay, is we have 81 pieces, and we're dividing those 81 pieces into 3 equal groups, which is 27. So for our first balance weigh, we would weigh 2 of these groups. And if they weigh the same, then we know the third group has the counterfeit. So we don't even have to weigh it. Or if they don't weigh the same, we can identify from that one weigh which one has the, which is the counterfeit group. So the first 2 groups are the same, so we know the last group is the odd man out. So now we're dividing that into 3 equal groups again. That 27 becomes 9, 9, and 9. And this, again, the same process. We would do our second weigh of 2 of those groups. And the same process, if they're equal, then the third group is odd man out with the counterfeit. If they're not equal, then it's identified right then and there which one is less or more. And then we would do the same process again, divide the group that's been identified with the counterfeit into 3 equal groups of 3, 3, and 3. And then do our third balance with 2 of those groups of 3. And whichever one, again, only one way, even though there's 3 groups we can identify. And then that last split would be 1, 1, and 1. So we're actually identifying the one counterfeit from this. So that would be our fourth and final weigh between 2 of these 1 coins on each side. And if they're equal, then the unweighed one is the counterfeit. If they're not equal, then it identifies it in that weight. So, and we know this to be true because we know that 81 is equal to third to the 4th power, because we're doing 3 groups. We're doing groups of 3. And we did that 4 times.
Awesome. Is that all you wish to say on this?
Sure.
Okay. I think everybody can
Unless anyone else in the group has something to add.
clap and say, yay, good job. So now, team 1, you challenged.
That was awesome.
Team 2 made a presentation. Team 1, you've got 2 minutes to discuss. If you think it's completely correct, you can say it's completely correct, good job, and we can move on. If there was something that was missing or something that was incorrect, you're commenting on the solution that was given. You're not giving an alternate solution or something else. And so team 1, discuss a little bit amongst yourselves to see if you saw any gaps in the argument or anything incorrect, and then decide if you're going, and then let us know if you're making a rebuttal.
Daisy, we came up with exactly the same, and so therefore we agree. And I don't know, Daisy, do you want to elaborate more on it?
Yes, actually, we talk about the similar solution. Actually, the same one. We just didn't get the illustration to that one, but it's actually the same process. So like well, it was mentioned at first, so after grouping them or dividing or separating them into 3 groups. So if the first 2 sets of groups, that means group 1 and group 2 do not, they do not balance, then we have to consider the third one then and figure out which one is actually, which 2 groups would actually balance, and then the group that which and the third one then would be considered to have the counterfeit. So I believe that our group would agree to that one because we actually discussed similar solution to that problem.
Can I add also something about the illustration? So it seems like 27, are they all equal? We're just talking about quantity. We're just trying to identify that the way of each group are equal. So 27 is just a figure. It can be a misconception for a student to see that 27 is not equal to 27. We're just trying to say that it should be in terms of their weight, not in terms of quantity.
That was actually a very good rebuttal point that I missed.
He's in our group, so he's giving more explanation.
So that wasn't so great. So let me share the screen and discuss briefly how I'm giving the points so you hear. The tech, the joy of doing the technology. Yeah. So over here, I'm making a scoreboard for us, and as the judge, I thought that the presentation was very good. I think it was actually completely correct mathematically. I think everything that needed to be said was said. A little bit in the graphics, I'll have a presentation note to comment about, or actually 2 presentation notes. I think one of the presentation notes is enough that the rebutting team could have gotten 1 point on the presentation notes, which I'll point out to that. But for the scoring, I'm giving team 2 all 7 points, team 1, there wasn't much to do because the solution was basically correct, and the judge I'm giving 0. The reason that there was 1 point coming out is I took a screenshot here of the presentation, and this line of 27 not equal to 27, if I was just looking at the graphics, somebody rebutting could say, hey, that is mathematically wrong. Well, it was the person on team 2 who pointed out that, hey, that wasn't quite right. Here on the graphics, the concept that was said, and so that's why you're getting points, but not written, was that what happens is, now I'm going to see if I can write on this thing with the color, is, okay, we start with the 81 and we divide it into piles like this. And then I might actually do something like draw a picture of the balance. And so that we're putting 27 here, 27 here, and putting this on the side, just to indicate where the balance is. And then once I have this, I would write out the 3 cases that could happen. And so if it looked like 27, 27, and then you just have the 1 on the side, then you would know that the lighter one, counterfeit, was here. If this thing's not moving well for me. If it looked like 27, 27, and 27, then you would know that the lighter one, and therefore the counterfeit, was here. And as the last case, if it looked like 27, 27, and 1 on the side was over here, then you would know that the counterfeit was here. And then you would iterate the process just like that. And so this is a very good presentation, full credit. Mathematical notation, there was room for rebuttal in talking about, hey, be careful with your notation that you don't do something that is misleading. But the rebuttal is supposed to be about the mathematical argument. So team 2, you just gave a nice presentation for problem 2. You get to challenge team 1 to a problem and they can accept or not. So take 30 seconds to discuss which problem you want to challenge them to and make the challenge. We hear problem 3. Okay, so team 1, do you accept the challenge of problem 3 or do you bounce it back? So I'll stop the share for a second. Team 1, what do you think?
We were still working on that, on number 3, and we didn't really come to a conclusion.
So this gives an interesting decision for you to think about. You take the challenge, say something, you might get some points on it, but they might get all 7 points in rebuttal by saying, hey, you were wrong because you didn't have an answer. By the way, the one case when you can say an answer in a rebuttal is if the first team doesn't give any answer at all. However, you could also say, no, we don't know how to do it, but we'll challenge you to do it, which makes it worth 10 points. If they secretly know how to do it, they could get 10 points instead of 7. So Anna's sharing her screen. Does that mean you're taking the challenge?
My teammates will chime in if need be. So
Anna, were you on team 2 or team 1?
team 1.
You're on team 1?
Yeah.
Yeah. Would you like, let me do a screen share. Let me steal the screen for a second because I think I have something that'll help. And I think you can annotate. So share screen, maybe let me just do this. So with this setup, I can click on colors and change them for you if that helps. And we can certainly write on this. You could annotate over top. Would this help you present?
Sure.
Okay. So I guess Anna's presenting for team 1, and I will start the timer now. And
okay. How much time do we have?
5 minutes.
Okay. Wait, what? 5 seconds?
5 minutes.
Okay, good. The first time I did this, I was eliminating, but I think I figured it out. So I counted the number of red, green, and blue. So I'm going to try to write here. There are 4 green. Oh, this is going to be terrible.
Can
you write instead? Okay, I could have typed 2. Okay. So there's 4 green, and then there are 5 blue and 10 red. And so as I was trying to figure out how to get them all to be red, I just started by combining the blue and the green. So since there are 4 green and 5 blue, I can combine 4. So 4 green and 4 blue make 8 more red.
So that means you want to combine a green and blue here and make it a red.
Right.
And so for instance.
So if you wanted to change 4 green and 4 blue to be 8 red.
So this is like I changed this green to red and this blue. Ah,
And while you're doing that, I'm gonna type, I think, so then if we do that, there would be 0, 0 green, 1 blue, and 18 red. That 0, I don't know how to get rid of that 0. Okay. So 0 green, 1 blue, and 18 red. And in order to make a red, you have to have 1 blue and 1 green. And so I thought, well, I could take the red and the blue to make a green, but then I would have 0 blue and 1 green. And so it just keeps bouncing back and forth, where I'll always have either 1 blue or 1 green left over.
I think so.
So I do not, or we, I don't believe that we can make them all to be red. So for blue, to all be blue, I'm going to start back with the 4 green, 5 blue, and 10 red. I would convert the 4 green and 4 of the red to be 8 more blue. So 5 plus that 8 would be 13. And so now I would have
0 green.
Yep. 13 blue and 6 red. And that still adds up to be 19 total.
Okay.
So now we have 6 red, and I need to have the same amount of green. And so if we take 2 red and 2 blue, that makes 4 green. And then that makes 11 blue and 4 red.
Mm-hmm.
And so then we combine the 4 red and 4 green to make
Yay!
8 more blue. So I do believe it is possible to make them all blue and not red. And I'll look at the question. Yep. So that is one process. I'm sure there's other ways to figure it out. Any other comments from the team 1?
I don't.
It's got to be blue because
Awesome.
blue
Awesome job.
is the only one that's an odd number.
Blue is the only one. So odd and even. Blue is the only one that's an odd number, which means what?
Okay, so that was your 5 minutes, and so now I guess that was a presentation by Team 1. Team 2 had
Done.
2 minutes to discuss the presentation to see if there was anything that, if they agree that it's correct, or if they have steps that were missing or incorrect. And then make a rebuttal. So we should also say yay.
Yeah, yay. I knew it had something to do with the odd number and the even number. Well done.
So
And-
two is discussing to see if they,
I don't know. Good. You got it. I don't know if we can challenge that. I think it's good. It's been done. We've done it.
Yeah, I would say you definitely got the step further that we could not get to. We definitely got to the first part that you had talked about where it's not possible for red, but we hadn't got to the blue. If I was gonna be picky, kind of like how David did with us, is just that transition on the 0 green to 4 green and the 13 blue to 11 blue and the 6 red to 4 red, is because there's 2 being taken from each of those 2 colors to, you know, annotate that in some way. So it's clear on, oh, this is how we got from 0 to 4. And, you know, just that little transition. Other than that, I don't know if anyone else has something to add. And I think about, like, when you were discussing, David, when you were talking about it, how to show it on the number 2 problem that we did, and now I'm thinking about it for this number 3 problem, I think about, oh, that makes sense, not only to be clear to the kids, but I think about how many kids are not in our classrooms on the day we do this. And then we say, oh, well, here it is. Don't you get it? You know? But there's like 3 steps in between each of the steps that we actually show that are not there. And so that's where I connected to, oh yeah, I should be showing, you know, visually what I'm verbally saying, because then it's there, or it's even if I ask another peer to explain it to, you know, each other, they have all the cues there too.
Yeah, certainly figuring out the answer and figuring out how to present it are 2 separate problems. And you know, as teachers, presenting things is very difficult. Showing your students how to present and talk and describe something is very hard. In fact, before the competition, we will sort of separate the students and we'll listen to the presentations and we'll give suggestions. We'll ask them to think about it and help them refine the presentations. In this, so any substantial math questions about the presentation that we just saw? So if not, I am going to give a commentary here. So the problem, you know, I'm going to see somehow the 2 pieces of software don't tend to work nicely at the same time when I'm doing the Zoom and the graphics program. They're not working in cohorts together, but I'll give it a try. So there were 2 parts. First is, could you change it into all blue? And I think that on a whiteboard with colored pens, where you could just erase a red one and a green one and then color them blue, you could have demonstrated that in 1 step. And then you notice that there was a shortcut here where changing the 4 green and 4 of the red into blue, making 8 more blue, doing it at 1 step is just doing 4 steps at once. I think we understood how you did that. That's sort of a mathematical lemma. Maybe something that would have helped in presenting that is if we put a little bit of algebra here, like let G equal the number of green,
Okay.
and then B equal the number of blue, and then R equal the number of red. And that works great for algebra in the high school thing. Then what you see is in this first process, we could take green, blue, red, and we translate that into something that would look like green minus 1, blue plus 2 and red minus 1. The point being, we get rid of one green one, we get rid of one red one, and we add 2 blue ones. And so then if you do this, if you repeat, can get things like green, blue, red goes to green minus 4, blue plus 8, red minus 4, which is exactly the step that happened from this 4, 5, 10 to 0, 13, 6. And there's similar moves for if you take the green minus 1, blue minus 1, red plus 2 would be impossible. In fact, the place where I'm going to give substance is Anna gave the correct answer that it's not possible to make them all red. But her argument, the way I heard it, was basically she made one set of moves saying, all right, try to make them as many red as possible, but then there's a blue left over. And it wasn't completely clear that what she said covered all possible ways of getting there. Mathematically, there's something known as an invariant, which you certainly see with even and odd. Let me come up here and make this a little wider if I can, and add something. Let me call this green prime, blue prime, and red prime. And so after you do the move, the number you get will be the same variables with a prime on it. And then what I'm going to notice is that if I take the number of blue primes minus the number of red primes, well, that's b plus 2 minus the quantity r minus 1. Which is equal to b plus 2, distributing the minus r, plus 1, because it's a minus minus, which is b plus b minus r plus 3. Right? And what this means is that the difference between two colors is always going to be the same, is always going to be a multiple of 3. It'll always change by 3. Because when I subtract 1 from one color, I subtract 1 from the other color, or I add 2, making the difference between 3. And what that means is that if we were trying to get this all the way down to all red, that would mean that we would have to make these 4 greens and 5 blues both turn into 0. But if I take the 5 blue and I subtract the green equals 4, we get b minus g is equal to 1. That would mean any other time we do these moves, the blue minus the green has to be 1 plus a multiple of 3. So it's not an even odd thing. You know, B double prime, you do it as many steps as you do, minus green double prime has to equal 1 plus, plus or minus 3 times some number n. Does that make sense? And so this is a case of an invariant. You're figuring out what the remainder of the difference is when you divide by 3. And so, for instance, when we came up to here, if we take 19 minus 0, if we take the blue, let's do the case where we did it, where we made it all blue. If I take 10 minus 4, 10 minus 4 is 6, which is divisible by 3. That's why this first case was not there. So what this means is, I don't think I'm sharing the full screen. I'm going to share the full screen here in a second. I'll share the scores. So on this one, this was problem 3, right? Here we go. And oops, that's not the one I wanted to collect. Let's get this one. So this is problem 3. Team 1 answered it. It was actually a good answer, but I think you could have put some more details into why the one case was not possible, why red was not possible. And so I'm debating how mean I want to be as a judge. Just to be fun, I'll go meh and be mean to you, and I'll steal 2 points. The rebutting team didn't say anything that was incorrect about it. And so it's not that what she said was, it's not that Anna said anything that was wrong, but what she said was not complete. Does that make sense? Why I'm judging it this way?
David, can I add something?
Yes.
I was thinking about, as was Anna was actually said about the number of colors for each, or the amount for each color. It actually helped me to figure to actually realize that green, when you pair up, that you need to actually focus on green and red first to change some of them into, combine blue and red to get another green.
Yeah.
Because if you combine red and green, you will get the blue. So there are 10 red colors and four green colors. So if you could make 8 red and 8 green, and that would be enough numbers for them to pair up to become a blue color. So I actually tried doing that one. So the first thing I did, I tried pairing up 11 and 12, and those 2 colors would become green. And then the other pair I did would be 15 and 16. So that's red and blue again. They would become green. The 2 colors would turn into green. So after those 2 steps, I would be able to get 8 red and 8 green. So there's enough partner for them. So the red and the green. So if you pair up red and green, so that would be a blue. So all of them will all turn into blue. Actually, I did 1, 2, 3, 4, 5, 6, 7, 8, 9. After 10 steps, I was able to make all of them blue.
Yeah, I think that's the essence of that is the same solution that Anna gave. And so I think we're understanding the problem, and we're making very good progress on this. When we do this, I will comment as we're going along that we feel that a wrangle is at the right level if the judges come in second. Our rationale for that is if the judges come in third and don't collect any points, then maybe the problems were too easy and the students didn't have to work hard enough, and we could have given them harder problems. If the judges came in first place and collected most of the points, then the problems were maybe too hard. And so Team 1 just presented, and so now Team 1 gets to make a challenge to Team 2, and Team 2 gets to either accept the challenge or bounce it back. And so, how are we doing here time-wise? Are we supposed to end? Oh, that's wrong. And so examples. Oh yeah, go ahead, David.
I'm trying to figure out number 4.
Uh-huh. One thing we could do
No,
is just talk through number 4 together if you wanted.
we could, or I'd like to see it solved or have some time to solve it myself.
Let me at least tell one bit just to describe, because I'm not sure I talked well about what the taxi cab distance was. And so that might make it a little bit more fair. Let me,
It must be 1, 2, 3, 4, 5. It's got to be, I don't know. I'm guessing each one of those points is like any other point, and I don't know.
so
From one corner to the other side, one corner to the far side would be a taxi cab distance of what? N?
so let
I
me
don't
see
know.
if I can
Go ahead.
mark this off here and make this work on this. Okay, maybe this is going to work.
Okay,
So if I click
I guess
over,
8.
so let me try to do it. Oh, you know what? If I break this, that might do it. Object, ungroup. And so, for instance, if I want to know the distance from this yellow one to this blue one, the taxi
4.
distance, you count how many lines you cross. So when I go from here to here, I cross 1, 2, 3, 4. And so the yellow and blue have a distance of 4 apart. And so this is very much like John talked about. You go from one square to another square, always in the same direction, always east-west. So you always either go east, always go west, and then always north or south. You don't go back and forth. So I'm not going to go up here, over, down like that. That's a longer path, and no diagonal paths were made. So now in the parking garage, we put pillars here so that you couldn't go through the corners. And so the point would be that if somebody hid this, so in old versions of Windows, they used to put games, and they had a game called Minesweeper, and it was very similar to this, where they would tell you how many things were adjacent. People are saying I have to go. I understand if you have to go. I'm hanging out for people who want to talk. But for instance, if I secretly put the treasure on the blue square and David guessed the yellow, I would tell him that it was 4 units away. But just because I've told him it's 4 units away doesn't tell him for sure that it's in this square, because it could have been in...
Could have been there.
Could have been this square is, I think, 4 units away, because you can go 1, 2, 3, 4. I think 1, 2, 3, 4. This one, oops,
No. There.
there is 4 units away. I think it's kind of interesting. I think this one is 4 units away. So just saying that it's 4 units away from one square doesn't entirely tell you the answer. But then if he made another guess, he might be able to narrow it down.
Well, it does define some diagonal parameters.
Yes, and that's a good idea. And so thinking of what square you might guess first can help. And so in fact, I don't know if you want to try making a first guess and seeing what happens on one of these grids. I can unbreak this, see what it would be in terms of parameters.
I thought first to choose one of the four in the center, but that would just leave to confusion, I think.
Uh-huh. So
You
what
know,
else?
I don't know. I would maybe choose one of the corners.
Sure. And so one of the things that you could think about that would get you started is if you guessed this upper left corner, let's see if I can get this to, okay.
I don't know.
So let me ungroup it. And so for
Is that
instance,
what we're doing?
if we chose this one as our guess, then what is the distance between this square and itself? So if the treasure was in that corner, what would the distance be?
0.
Sure. And if it was in this square, what would the distance be?
1.
Yeah. And if it was in this square, what would the distance be?
1.
Uh-huh. If it was in this square, what
2.
would the distance be? You're starting to see a pattern. If it was in this square, what would the
3.
distance?
2.
And here.
Yeah, there you go. All right. So that defines that diagonal parameters.
Yeah.
3,
And so
3, 3.
in one guess, when I tell you the distance, you at least know which diagonal it was on. So does that give you a hint about what you might do for your second guess? All you need to do is figure out, if you knew it was 3, you would know it was one of these 4, and so then you just need to know what it is.
Do I pick another starting spot?
Like sure. So what would another starting spot
Pick
be?
another corner.
Sure. And so
And
if
then
you
it's
pick-
done too.
Yeah. So for instance, if you picked this
Bingo.
corner
That's
here and you made that green, I could then maybe put the text in a different color. Oops, nope, that's not what I wanted. I'm sure there's a way to make a colored text. Nope. Oh, what happens if I do that? I'm just testing here. And yeah, so I could make colored text. So like in that case,
Yeah,
this one would be 0, which I could color there. This one would be 1, which I
Have
could
the same
color
delineation.
there.
Right.
This would be a 1, which I could color.
That's it. It's done.
Yeah.
It's
And so-
solved.
Well, does that completely solve it? So this shows you that you could find it in 2, but does that prove to you that 2 is the smallest number that you could find it in?
2.
So mathematically, there's a question here in that, so I'm sure there's some way to do that differently. Yeah, so you see I could color this grid with the 0, 1s, 2s, etc. So when you need to show that something is the minimum possible, Selena, I see you have a question. What's your question? Selena? Yes. What's your question, Selena?
Oh, nothing. I was just, I don't know what I'm doing.
You just clicked it.
I was trying to type thank you at the bottom part.
I see.
I don't know what's going on with my laptop. Sorry.
It's all good. I just didn't want to miss a question.
Yeah, thank you.
You know what, that's the solution, because each of those cells is uniquely addressed.
Right. But to make the solution mathematically to show that you have a minimum means you need to show that you can do it. So this shows that you can do it in 2, but you also have to show that you can't do it with fewer. Does that make sense? So you need to show that you
Yeah,
can't
can do it
0.
with fewer.
And so
One.
if you have 0 guesses, you can't possibly know. And so then you have to show that you can't do it with 1 guess. But no matter what you guess, like if you guess this corner, there's going to be 2 possibilities that it could have been
Bingo.
1. So if it was in those, and any other, no matter what square you guess, you can always find at least
There's
2
multiple
squares.
possibilities. Yeah.
Right.
Yeah,
So
that's the only way to name it, with unique addresses.
Yeah.
Nice. Yeah.
Okay.
Describing your
So
answer to.
I drew 2 number lines side by side, and then I started, I think it broke into 5 parts. One side is the Phoenix to Page, and this one here is from Page to Phoenix. And since the person left at 11, I made my number line to the time that they drove to Page, they arrived at Page. Same thing with the Page. I started off with 12, and then 12, 1, 2, 3, 4, and then the arrival time in Phoenix. And then the time that's closest to each other is 2 o'clock. So that's how I got my answer.
Do other people in the room agree with Melissa's solution? Does this convince you that it's 2 o'clock that they pass? Could the other team rebut and point out anything that was wrong or not said? So I think this means that we've got Melissa. Yeah.
Yeah, I got it right.
By the way, we've got a second solution to the problem given with equations and variables. This is Daisy. So here's actually a discussion point. Is it easier to present Daisy's solution or easier to present Melissa's solution? You only need to present one solution. And so this is a thought. What do people think? Are there any thoughts on the comparison between Daisy's solution versus Melissa's solution?
For me, it's my solution. I'm more visual, and all that numbers kind of crossed my eyes. So that's for me.
Any other thoughts on the two solutions? Actually, I think there's a pedagogical thought here that I'd like to share with people. Melissa's solution was something you could do without algebra. And it very much shows you how to solving algebra story problems with pictures and logic before students take algebra in grades 5, 6, 7 is very, very useful. It gets them more comfortable with what's going to happen when they have algebra. But somehow, after you really get good at algebra, algebra becomes a machine that very quickly can solve problems if you've mastered it, as Daisy explained in her solution to the problem. So there's a role for both of them. I think the notion of which solution is better depends a little bit on your mood and on your background. Certainly a student that had not seen algebra would not make any sense out of Daisy's solution. I think anybody would make sense out of Melissa's solution. I'll comment that, you know, I'm a professional mathematician. I do algebra all the time, but when I solved the problem, I did it exactly like Melissa did. It was my first instinct was just to draw a picture and see what happened. The time when the algebra would really become useful is if it was at 12 minutes after 2. You wouldn't discover that so easily with a picture.